Hi, and welcome to the session on automating ML workflows in secure environments. My name is James Park. I am a solutions architect on the AWS Worldwide Public Sector Federal Partners team. I'm also joined by senior solutions architect Nathan Arnold. Today we'll be covering general MLOps principles and diving deep into how we can automate our ML workflows in regulated AWS cloud regions, such as in FedRAMP High approved AWS Gulf Cloud regions with both cloud native and open source tools. Our ultimate goal for this session is to help architects and developers design an MLOps architecture for your organization in the elevated AWS cloud regions. To quickly go over our agenda, first we'll be introducing a few different concepts that represent an effective MLOps strategy. We'll try not to spend too much time on the details beyond the scope of what an architect or developer might need to know. We'll talk about why MLOps is important, how it can be a challenge, and then spend the majority of our time talking about the specific cloud native and open source tools that can help us automate our ML pipelines in AWS. At the end, we'll discuss functional reasons to use which tool and when. So let's begin by laying the groundwork for the machine learning process. We want to understand that ML is a continuous, iterative process. This is why MLOps can be so useful for so many teams and organizations. Let's take a look at a simplified view of a generic ML process to better understand. So typically, the ML process begins when you have a business problem that needs to be solved, and ML has been determined as the correct solution. Initially, a data scientist will likely spend a good chunk of time collecting, integrating, preparing, cleaning, and analyzing data to support a future model that may solve the business problem. In most cases, the data needs to be further processed through feature engineering, the process of extracting features from raw data that could be used in supervised learning. Next, the model needs to be trained while a data scientist tunes parameters for the selected model type to be ready for evaluation. And depending on the results of this evaluation, it is quite common to have to go back and collect more data or perform additional processing until the model is achieving desired accuracy and/or meeting business goals. Once the model is performing as desired, it is ready to deploy to production and can finally be used for inference or for predictions. The final step, and a very important step, is to continuously monitor your model in production. Models can frequently become out of date or become less accurate over time due to data inputs, a change in the relationship between the input and the output, or any number of reasons. By continuously monitoring your models in production, you will know when it's time to retrain the model or gather new data to augment the model. This process shown here can initially start out as an entirely manual workflow, but as ML footprints grow within an organization, this process can become a huge bottleneck to innovation and ineffective in solving those business problems identified in the beginning. Having an operational process in place can alleviate some of these bottlenecks, which is of course where MLOps is relevant. So what is MLOps? MLOps is a set of operational practices to automate and standardize model building, training, deployment, monitoring, management, and governance. It can help companies streamline the end-to-end machine learning lifecycle and boost the productivity of data scientists and MLOps teams while maintaining high model accuracy and enhancing security and compliance. To illustrate what I mean, let's take a look at some technical AWS architectural diagrams without MLOps implemented and what pain points we might see as a result. Here I have a pretty standard data science setup. The data scientist has access to an AWS account with a SageMaker Studio domain where they're able to access Jupyter notebooks to develop their machine learning models. Data might be pulled from various sources upstream like S3, RDS, Redshift, Glue, etc. The models and their artifacts produced by the data scientists are then stored downstream in an S3 bucket. Now, this is fine for basic model creation, but unfortunately it often ends here. Gartner estimates that only 54% of machine learning POCs actually make it into production, and there are various reasons for this. Often, there's a misalignment between strategic objectives of the company and the machine learning models being built by the data scientists. A lack of communication between DevOps, security, legal, IT, and data scientists is also a common challenge, blocking models from reaching production. And finally, if the company already has a few models in production, a data science team can struggle to maintain the existing models while also pushing out new models. But what if a model does make it into production? Let's assume the data scientist is able to spin up a SageMaker inference endpoint to host the model, and the developer of an application is able to connect to this model and generate predictions through API gateway and a Lambda function to call the endpoint. What pain points can we identify in this architecture? Well, first of all, any changes to the machine learning model will require manual action by the data scientists in the form of rerunning cells in a Jupyter notebook. Not ideal. Second, the code that the data scientists wrote is stuck in these Jupyter notebooks, which is difficult to version and to automate. Third, the SageMaker endpoint may not have autoscaling turned on, so it cannot adjust capacity according to the number of requests coming in or to meet demand. And finally, there is no clear feedback loop. If the quality of the model deteriorates, you would only find out through complaints from disgruntled users. These are just some of the challenges which can be avoided with a proper MLOps setup. So now let's see if we can address some of those pain points by talking about what tools we can deploy in our AWS secure environments to implement an MLOps workflow. While there are many ways to automate your ML pipeline, the three solutions we will be discussing today that are available in regulated AWS cloud regions, such as in FedRAMP High approved AWS Gov cloud regions, are AWS Step Functions, cloud native solution, MLflow, an open source platform, and a third solution that combines Amazon EKS, our managed Kubernetes service, with Kubeflow, another open source platform. First, let's talk about AWS Step Functions. So what is AWS Step Functions? Step Functions is a serverless, fully managed, visually driven orchestration service that lets you build resilient workflows between various AWS services. To illustrate what Step Functions does, let's look at a simple example. Suppose we're building an application where we take photos and upload them to S3, and we want to do a few things with these photos, like create thumbnails or send it to Amazon Recognition to identify faces or things in the photos. Maybe I also want to write some metadata to a data store like DynamoDB. The left side of this slide here describes the functionality that I want, and the right side is the same functionality implemented as a state machine in Step Functions. We have representations of states that are tasks, states that are choices with branching logic, tasks that can throw errors, and tasks that can be performed in parallel, like generating the thumbnail as well as sending the photo to Recognition. And all this is done automatically as long as the state machine is properly defined. Now let's use a real SageMaker model deployment and approval pipeline as an example of how Step Functions can be used to implement an ML pipeline, in this case, one where we get human-in-the-loop feedback before models are promoted to deployment. So the way that this works is that when a model is retrained, it's dropped into an S3 bucket. That S3 bucket invokes a Lambda function, which starts the execution of a Step Functions state machine. And that state machine has been waiting for a new model to become available, as represented by the green arrows below it. And once a new model is available, the Lambda function, again, is going to construct an email and send through SES, which is Simple Email Service if you're not familiar with it. And it doesn't have to be SES in this case. It can send a message to an API or to a queue or however you want to design it. But in this case, it's an email that gets sent to a team of data scientists notifying them that a new model is available. Please review it and then determine whether this model is ready for production or whether to reject it. The response is delivered by clicking a link in the email, which sends a request to API Gateway, which then invokes another Lambda function, which is going to prepare arguments to give back to the state machine to let the state machine know which way it should go, approve or reject. And that's what you see in the orange loop. If it's approved, it's sent to another S3 bucket for downstream processing, perhaps into another pipeline or for another team to deploy it into production. So the key takeaway here for us is that Step Functions and its state machine is sitting in the center of all this, orchestrating the decision-making and a workflow for this decision pipeline, or the deployment pipeline. This isn't exactly how you have to implement it, but it is one use case when we want to design a pipeline that involves human input and how we'd be able to architect that. So here we have the internal workings of the state machine from the pipeline from the previous slide, the pipeline for reviewing a new model and getting human approval for it. And I want to emphasize that this visualization on the left is exactly how you'd see it in the AWS console. This is not a representation just for this session. So let's briefly go through the steps here. So at the top, we get the new model, which is likely in our case, the S3 bucket and file name for the model. Get manual review would trigger the Lambda function to send out an email to the team and get a response back to approve or reject the model, which then forks into two paths for approving or rejecting. Lastly, we see its corresponding code on the right written as Amazon States language, which is a JSON-based structured language used to define your state machine. So now let's look at another potential use case, the process of building, training, performing transformations on data sets using the trained model, and how we can operationalize that with step functions as well. So if you were to do this process with, say, a Jupyter notebook, for example, in a SageMaker notebook, you'd have to write the code to retrieve data, train the model, transform the data, etc. But it is, of course, a manual process that is difficult to replicate. This is similar to the process we saw in the earlier architectural diagrams, demonstrating what a pipeline without MLOps might look like. And of course, this workflow can be automated with step functions. And that would look something like this. So you have a state machine that retrieves data, it trains the model, it waits for the training to complete. And when the training is complete, if it succeeds, you go on to create a model and transform that data. And finally, if that succeeds, you can exit and you've accomplished your goal. But on this bottom row, you can, of course, go into different states of success or failure. So by inspection, you could look at that workflow execution and determine if it was successful or not. However, we can take this even one step further. I want to introduce the idea of running synchronous AWS Glue jobs within step functions, all without writing code. If you aren't aware, AWS Glue is a serverless data integration service useful for building ETL. ETL stands for extract, transform, load workflows. So if we incorporate that capability into the state machine from the previous slide, that workflow we looked at before goes from what you see on the left to something much simpler due to the native integration with Glue ETL. Okay, the next cool tool I want to talk about is MLflow. So MLflow is an open source platform for managing workflows and artifacts across the machine learning lifecycle, including experimentation, reproducibility, deployment, and a central model registry. This functionality is accomplished by a few different components of the MLflow platform. These are tracking, which gives you the ability to log and analyze model parameters related to the training of a machine learning model over time, evaluating performance of those models, and managing artifacts. Projects, which can help you package ML code in a reusable way to share or transfer to production or into different pipelines. Multiple projects can even be chained together into workflows. Models, giving you the ability to package and deploy ML models for use downstream, such as serving an endpoint or batch inference. And registry, a centralized model store that provides functionality like model versioning, model aliasing, model tagging, and annotations. So to demonstrate the power of MLflow, I just want to walk through a sample architecture that leverages the functionality of this tool in an ML pipeline. So you would start by setting up a central MLflow tracking server during your ML project. You use this remote MLflow server to manage experiments and models collaboratively. In this case, MLflow is hosted with AWS Fargate, our serverless compute engine offering for running containers in Amazon ECS or Elastic Container Service. An MLflow tracking server needs two components for storage, an artifact store and a backend store. We use an S3 bucket as our artifact store and an Amazon RDS for MySQL instance as our backend store. The artifact store is suitable for large data and is where data scientists might log their artifact output, for example, models. In this case, MLflow natively supports Amazon S3 as an artifact store. The backend store is where the MLflow tracking server would store experiments, run metadata, as well as parameters, metrics, and tags for runs. MLflow supports two types of backend stores, file stores and database backed stores. And in our case, we're using a database backed store. So this simple architecture already provides many of the functionalities mentioned in the previous slide. Just by building this, we can, as previously mentioned, track experiments running on SageMaker with MLflow, register models trained in SageMaker in the MLflow model registry, or deploy an MLflow model in a SageMaker endpoint. all by simply deploying MLflow into Amazon ECS and reaping the pipeline features of MLflow while maintaining the managed operational benefits of AWS. All right, now I want to pass it off to Nathan Arnold to cover our next solution, Amazon EKS and Kubeflow.
Thank you, James. Again, my name is Nathan Arnold. I am a Senior Solutions Architect here at AWS, and we're going to take a look at one last tech stack today with another open source project, Kubeflow, hosted on the Amazon Elastic Kubernetes Service, EKS, as another option for building and running your MLOps pipelines. But first, let's try to answer the question, why would we want to use containers for machine learning? Well, if we think about all the tools that we might need, things like scikit-learn, pandas, or NumPy, and if we think about the libraries we might want to use, things like PyTorch or TensorFlow, or drivers we might need, things like Intel's math kernel library or GPU drivers from the NVIDIA CUDA toolkit. And then you add to that any training scripts that you might need. What you end up with is a lot of dependencies, a lot of different versions of things, and you need a way to package all that in a consistent and modular way. And that's really where containers come into the picture, because they allow you to package up your training code, your dependencies, and configurations into a unified deployable artifact. And because you're locking in dependency versions and bringing only what you need to run your code with you baked into your container, this makes your ML environment more lightweight, more portable, independent of the underlying host, and more scalable at the process level, and ultimately more consistent regardless of where you choose to run your containers. And to make it easier for you to get started leveraging containers for machine learning, the AWS Deep Learning Containers are available as a set of pre-packaged Docker images for training and serving models in TensorFlow, PyTorch, and MXNet that you can further customize and use with different services like Amazon SageMaker and Amazon Elastic Kubernetes Service, EKS. They include the NVIDIA CUDA drivers for GPU instances and the Intel math kernel library for CPU instances, and you can pull them directly from the Amazon Elastic Container Registry when you're ready to get started. Now, with any discussion about containers, you eventually have to address container orchestration and how you're going to manage your modular microservices at scale. And of course, Kubernetes is the de facto open source standard for container orchestration engines, and there's a whole universe of related topics. But at the end of the day, Kubernetes allows you to run various control loops that take into consideration the desired state of your workload compared to the current state of your workload by observing the current state and making the necessary adjustments so they match. Another way to break Kubernetes container orchestration down is to consider the control plane, which acts like a conductor, and the data plane, which acts like the orchestra. And much like a conductor, the control plane observes the containers that are running on the data plane and then orders the necessary adjustments based on changes to the desired state. But even still, why would we want to use Kubernetes for machine learning? Well, Kubernetes gives you the ability to build more complex ML pipelines by composing or combining smaller, reusable components. It enables portability by providing a standardized abstraction layer across different environments on premises and in the cloud. And Kubernetes provides a flexible and automated framework for managing the deployment and scaling of your containerized applications. But of course, if you have any experience with Kubernetes, you know that setting up and maintaining a cluster can be challenging and resource intensive. Which brings us to the Amazon Elastic Kubernetes Service. As a managed Kubernetes service, EKS provides you with a fully managed, highly available control plane. You can interact with the API server using kubectl. And for the data plane, which resides in your own virtual private cloud environment, you can deploy EKS managed node groups for automated provisioning and lifecycle management. You can deploy self-managed node groups if you need to use customized machine images. And in standard regions, you can leverage serverless compute capacity through AWS Fargate. And EKS is really designed to make it easier for you to set up and manage Kubernetes clusters by taking care of much of the operational overhead for you. But how does Kubeflow fit into all of this? Well, if we're leveraging EKS to help us set up our compute infrastructure, and we're thereby working within a Kubernetes environment, Kubeflow is just another application that we deploy onto our Kubernetes cluster to make it easier for us to orchestrate our machine learning workloads. Kubeflow itself comes with many different features, including a central dashboard, hosted Jupyter notebooks, training and serving features, as well as pipelines, which is what we're going to focus on today. Kubeflow pipelines are made up of various components that represent the different steps in your workflow. Each component includes its own metadata, its own inputs and outputs, and a container implementation that pulls either a base image or your containerized code from a container registry. And then the code for that component is executed at runtime inside that container. And then the outputs from a previous step can become the inputs for the next step, and so on and so forth, until you chain the necessary components together to get the desired ML workflow. There are several different types of components supported in Kubeflow. You have your Python components, which are further subdivided into lightweight components that are basically self-contained Python functions. Again, this Python code is extracted and executed inside a base Python container at pipeline runtime. You also have containerized Python components, which allow you to handle more complex dependencies. So in this example, we're breaking out the addition functionality into a separate add numbers function, and then we're importing it and referencing it inside our component. So you can actually reuse that function definition over multiple components. Container components, not to be confused with containerized Python components, are ideal if you want to pull in an arbitrary container image. For example, if you've prepackaged your execution code in a container and you want to use that in a component. And so you can specify your image and also pass in any commands or arguments directly with container components. Now, I mentioned that usually the outputs from previous component executions become the inputs for subsequent component executions. But there are special cases where you might need to import artifacts that are outside of your pipeline. And that's where importer components come into play by allowing you to target artifact URIs. And actually, you don't need to write an importer component. It can be imported from the DSL module and used directly in your pipeline, as you see in this example here. So now that we've looked at different types of pipeline components, how does that all come together to compose a pipeline, and how do we execute it? Well, in this example, we have three different components: square, add, and square root. And we can reference these components in our square and sum pipeline definition. But we can take things a step further and reference the square and sum pipeline in another Pythagorean pipeline definition. So you can see there are multiple ways for us to reuse both components and pipelines in our workflows. And we can also control workflows of our pipelines by adding various condition statements, looping, and exit handling. And then once we're happy with our pipeline definition, we can compile it into YAML format using the Kubeflow SDK, and can then share and reload components and pipelines using that same YAML format. And then run your pipeline either from the dashboard or using the SDK or the Kubeflow CLI. And in addition to your native components, you can also leverage the Amazon SageMaker components for Kubeflow pipelines to offload many of your ML tasks to Amazon SageMaker rather than running those tasks directly on your EKS cluster. There are several SageMaker components that are available today that allow you to execute training jobs, hyperparameter tuning, or batch transformation on SageMaker. You can also integrate SageMaker ground truth for data labeling. So even with Kubeflow, you're not limited to just your EKS Kubernetes cluster. You can reach out and take advantage of the features available through Amazon SageMaker as well. Here's an example of the SageMaker training component as part of a training job pipeline definition. So you just load the component from the Elastic Container Registry, reference it like this in your pipeline definition, and pass the necessary parameters like the region you need it to run in, your algorithm spec, where your input data is, where you want your output data to land, and the permissions that you want the component to have. These SageMaker components work in tandem with the AWS controllers for Kubernetes, specifically the SageMaker controller. So under the hood, the training component is going to create a training job definition based on your inputs, and that training job is a custom resource that the SageMaker controller manages. The Kube API server gets the request to create a training job. It updates the state record in etcd, and then it lets the SageMaker controller know that a training job has been requested. And then from there, the SageMaker controller contacts SageMaker to kick off the training job. So not only can you leverage Amazon EKS to help you manage Kubernetes clusters and Kubeflow to help you define ML pipelines, but you can also augment your pipelines with SageMaker components for features like data labeling, hyperparameter tuning, and distributed training jobs as well. Okay, so we've looked at AWS step functions, ML flow, and Kubeflow as different options for automating your MLOps workflows. But which one should you use in your ML environment? Well, if we start with AWS step functions, it's going to be a more serverless option for your workload orchestration, which results in less code to write and maintain. There are no servers to configure or manage. You get high availability and fault tolerance by default. There are built-in features like state machine visualization, error handling, timeouts, parallel processing, and access to execution history that you can leverage out of the box. And overall, AWS Step Functions is going to give you a more cloud native experience with built-in integrations to other AWS services like Amazon SageMaker. ML Flow, on the other hand, is essentially a Python program that data scientists can use anywhere in a cloud agnostic way to track their experiments and version control their models. Compared to Kubeflow, it is easier to set up, but it also integrates with Kubeflow as well as an experiment and model tracking augmentation option, with the model registry as the core component to help you manage your ML lifecycles. And it's really a good fit for a small team of data scientists who are looking for a better way to organize themselves around their experiments and model versions. And then finally, with EKS and Kubeflow, you're building on top of Kubernetes and container orchestration to enable workflow automation, which gives you some increased portability because you can run Kubeflow wherever you can stand up a Kubernetes cluster, but it can be more complex to set up and manage the pipelines that you want to use. So it's really a good fit for larger teams that have standardized on Kubernetes and have that in-house expertise and really have a need to manage more complex ML lifecycles. But as you can see, there are several different options available, and of course, AWS can work with you to architect the solution that best fits your needs. Okay, to wrap up, on behalf of James and myself, thanks again for joining us to explore options for automating ML workflows in secure environments like AWS GovCloud, secret and top secret regions. We hope you learned something useful today. If you're interested in learning more about the solutions that we outlined, check out the links in the notes section below. And for all of us here at AWS, we look forward to collaborating with you as you build out your MLOps pipelines. Thanks again.